All right, welcome back, everybody. So, we are here now to start Chapter 7. So, I'm going to make this the first half video for Chapter 7. It's our second chapter on enzymes. Enzymes, mechanisms, and control. Please bear with me. I'm making this video sitting on my bed, trying to hide from my very noisy dogs. So, if you hear them in the background, I apologize. I'm also surrounded by a mountain of stuff here: notebook, iPad, laptop, and book. So I might shuffle around at any given moment to try to find a resource that I need. If there's any awkward pauses, I apologize for that. All right. So let's continue our discussion of enzymes. So this is a new chapter, and so the last one sort of introduced enzymes and then also talked more about enzymes that followed what we call the Michaelis-Menten model of kinetics, right? So within that chapter, we saw a contrast, a couple of examples. We saw chymotrypsin, which was Michaelis-Menten, and then another one, ATCase, which was not. That was what we call an allosteric enzyme. And so we're going to talk more about those specifically in this chapter. All right. So just to refresh, what are allosteric enzymes? Well, basically, they're enzymes that are going to exhibit what we call cooperative effects. They definitely do not follow Michaelis-Menten kinetics, right? So in a kinetics curve, an activity curve, instead of giving the Michaelis-Menten hyperbolic type of shape, right, it gives them more that S shape, sigmoidal. That's pretty characteristic of an allosteric enzyme. Excuse me. So basically, what it means to exhibit cooperative effects is that when something binds to that enzyme, it fundamentally changes its, not its chemical structure, but its physical structure, its folding patterns, its geometry, its angles, right? So whenever something binds and causes this shift, that can affect its future activity, right? And this can mean increasing maybe its activity or tendency to bind a substrate, or decreasing it, right? Um, so there's all sorts of things that you can add to them. Substrate binding themselves can cause allosteric effects. Also, inhibitors and activators can cause allosteric effects as well. Uh, one thing that you frequently see with allosteric enzymes is that they're actually involved in what we call feedback inhibition mechanisms. So what the heck does this mean? Sorry, I'm coughing a bit today. So, as you'll see, once we start talking more about metabolic reactions later in the term, um, our body is just one big assembly line, right? You have all these metabolic processes, and there's several steps in each. So one has to be completed before you go to the other, to the other, to the other. So there's lots of different stages along the way. And if you're trying to go from point A to point B, you're going to have a lot of stops in between where you have these little intermediate products that aren't necessarily the final product, but they do exist for a period of time. And the presence of these can have allosteric effects on enzymes. Let's talk about ATCase. This is one that we mentioned back in the last chapter. We said ATCase was a non-Michaelis-Menten enzyme, and it is. It's an allosteric enzyme. And its purpose was to basically promote this reaction. Again, as I always say, sorry for the iPad cutting off photos, but look for this picture in your PowerPoint on your computer or in your book, right? But basically, it catalyzes this reaction. That is a condensation reaction between aspartate and carbamyl phosphate, right? So basically, it promotes the reaction of these two compounds, and then that reaction, or excuse me, that product that's made can then sort of keep on going down the assembly line until you ultimately make CTP and UTP, which are then used further on for building of nucleic acids. All right, so we can see examples of allosteric effects here, right? So CTP, like I said, is sort of one of the touchstone products here. It's one of the touchstone products in between the original starting point of aspartate and carbamyl phosphate, and then ultimately synthesis of nucleic acids, right? So let's say you're going through this whole assembly line process, all these reactions, and for some reason there's a bottleneck at some point, and you end up having sort of a barrier where you start building up a bunch of excess CTP, right? Well, if you have excess CTP, that means that that CTP is not being used for further nucleic acid assembly, right? And in other words, you don't really need any more if you already got a lot of it, right? So CTP is actually an allosteric inhibitor for ATCase. Excess CTP can bind to ATCase, and that makes its activity go down. So it's not catalyzing this reaction anymore, or at least not as nearly as much, right? So the presence of CTP can basically kind of shut down this assembly line. And again, if you look at the photo that's indicated here, you can see a nice little diagram of this. That product sort of loops back to the original place where you start getting that original activity, and that's where ATCase is, and it shuts down the assembly line. Right? Eventually, you'll get to a point where, excuse me, I'm really coughing today. I don't know why. Eventually, you'll get to the point where CTP is needed, and it can detach from your ATCase, go back into the assembly line, and then things can start back up as needed, right? So that's a really good example of how you see something called feedback inhibition a lot of times with allosteric enzymes. And that's an organism's way of naturally saying, hey, we already got enough of this, we don't need to make any more, we're going to shut down the assembly line for the moment. You can also have activators that are made in this way, right? A lot of times you might have an enzyme that is sort of naturally inactive in starting a metabolic pathway, but whenever some other product is made, that sort of acts as a signal to start the new assembly line, and that can bind to an enzyme to activate it, right? So feedback loops, feedback inhibition, and activation are present in quite a few metabolic pathways. Okay? And again, you can't really see this picture very well, but again, refer to the one in your book or in your on your computer. So if you look at the effect of inhibitors and activators on ATCase activity, and this is a kinetics curve, right? So we already said previously that the normal kinetics curve for ATCase is sigmoidal. It's definitely not Michaelis-Menten, right? Substrate concentration will cause a slow increase until you hit to a certain amount. Then it causes a larger increase before it levels out, as opposed to the Michaelis-Menten model, where even adding small amounts of substrates cause a large jump. One funny thing, though, about this curve can become either more sigmoidal or less sigmoidal, depending on if you have an inhibitor or an activator present. If you look at the middle line, sort of the blue one, I believe, that's the control. That's where you have no ATP or CTP present, right? No activators, no inhibitors, and that's its normal activity curve, normal sigmoidal activity curve. You have large amounts of CTP present. Remember, CTP is a feedback inhibitor. And you can see what happens is that curve will actually become more sigmoidal. It flattens out more at the beginning, and it takes a longer time for it to eventually reach its Vmax. Whenever you add these activators and inhibitors to ATCase, no matter what, you will always eventually get to the eventual Vmax. It's going to be the same as it was in the control. It's just going to take you longer to get there if you have an inhibitor, and it's going to take you a shorter amount of time to get there if you have an activator. If you look at the red curve, The red curve is what happens to ATCase, whenever there's large amounts of ATP present. ATP is an activator for ATCase, right? It increases its activity. And you'll notice, look at the shape of the curve. It's almost hyperbolic. It's very similar to the ones that we saw with Michaelis-Menten enzymes, right? So actually, as you add an activator to ATCase, it almost, not quite, but almost exhibits Michaelis-Menten behavior. You get to your Vmax at a lower substrate concentration than you would have without the ATP. With inhibitor, you have to have a larger substrate concentration to get to your Vmax, right? So Vmax overall is unchanged with ATCase, no matter what, whether you have an inhibitor or activator or nothing, but it takes a larger amount of substrate with an inhibitor and a less concentration of a substrate to get there with the activator. So here's an interesting little thought question to ask you. So, what does this say about the nature of the inhibitor? So focusing on CTP, the inhibitor, if we still get to the same Vmax, but it takes us more substrate to get there, what does that tell you about the nature of the inhibitor? Well, we talked about, in the last video, inhibitors being competitive or non-competitive, right? And in that video, what did we say? A competitive inhibitor, with a competitive inhibitor, you eventually get to the same Vmax, it just takes more substrate to get there. With the non-competitive, we never get to the same heights of Vmax as we would without. Since we're getting to the same Vmax here, I think it's pretty safe to say that CTP is a competitive inhibitor of ATCase. And you can tell because we can still get to the same Vmax. All right. This slide just shows the reaction, the initial reaction catalyzed by ATCase. I'm honestly not that concerned about you guys, really knowing the structure and mechanism or anything like this right now. Later on, maybe, if we get to it. But I just kind of wanted you to see what it actually did. All right. So, we're going to start introducing a little bit of terminology here. So just like we had terminology for the Michaelis-Menten systems, we also have terminology for these allosteric systems as well. So one term that we don't use is K sub M, right? That's because the M in K sub M standard for Michaelis or Michaelis-Menten, right? Obviously, these aren't Michaelis-Menten enzymes, so we have to use a different terminology. We use K sub 0.5. Creative, right? It basically means the same thing that Km did with Michaelis-Menten enzymes, right? It's the substrate concentration of an allosteric enzyme at which you attain half of your Vmax. All right? Also, we want to introduce a couple of terms here. K systems and V systems. So this refers to basically system. This is analogous, really, again, to Michaelis-Menten. K systems are analogous to what we saw with Michaelis-Menten competitive inhibitors, right? In a K system, the K. Let me backtrack. With Michaelis-Menten, with competitive inhibitors, the K sub M was altered, but not the Vmax, right? We basically have that same situation over here, but we call it a K system in context of allosteric enzymes. So in an allosteric enzyme system, a K system is referred to one in which the K sub 5 of 0.5 is altered by inhibitors, but Vmax is unaltered. So you can basically think of a K system as being kind of the same thing as a Michaelis-Menten enzyme system with a competitive inhibitor. And as you might expect, a V system is analogous to the Michaelis-Menten systems that had non-competitive inhibitors. Vmax is artificially lowered. You're never going to get there. But the K sub 5, K sub 0.5, sorry, remains the same. And this is analogous to what we saw with Michaelis-Menten, where K sub M remained the same, but Vmax was lowered. A lot of confusing terminology here, I know. But really, the definitions are the same. We're just kind of changing the terminology that you use. So it's just you just have to know which ones to apply to which systems. All right. So let's take a look at the major models, and there's going to be two major models of allosteric enzyme behavior. These are referred to as the concerted model and the sequential model. All right. Again, let's take a step back and remind you of the whole point of allosteric enzymes. We said allosteric enzymes, when something binds, and that something can be a substrate, it can be an inhibitor, it can be an activator, whatever. When something binds, it causes an essential conformation shift that makes the enzyme either more likely to bind a substrate or less likely, right? Whereas with Michaelis-Menten, it was all or nothing. It either binds it or it doesn't. All right? Well, there's a couple of different models, a couple of different theories for how this occurs. In the concerted model, all parts of the enzyme, all subunits, everything, exhibit a conformational change at one time. So something binds to that enzyme, the whole thing shifts. The whole thing changes shape. All right? Sequential model, what happens is something will bind to an enzyme in a subunit. It'll cause that subunit to change conformation. Once the subunit changes conformation, then, and only then, does the conformation of another subunit change, and so forth. It's much more of a domino effect there, instead of it all happening all at once. Both of these occur. Some allosteric enzymes will follow the concerted model, some will follow the sequential model. All right, and so, I apologize, this is going to get sort of in the weeds and a little bit technical, but I'll explain it to the best of my ability, and feel free to let me know, as always, if you have any questions or need help understanding what I'm saying. All right, so we're going to focus on the concerted model first. Okay, and so in the concerted model, basically, there's two conformations that it has. All right, it's got an R what we call an R conformation. R stands for relaxed, and T conformation. This stands for taut. And this is a little counterintuitive, so make a mental note here. The R binds substrate more tightly. That may not be intuitive since you associate R with relaxed, but the relaxed is just referring to the conformation. It's not referring to how tightly it binds an enzyme. So R has a high affinity for substrate. It binds it tightly. The T conformation has a low affinity for substrate. It binds it pretty loosely, if at all. All right, and so if you look at this photo right here, the one that's on sort of this middle slide here, this exhibits basically what you see with these two conformations at any given time. They exist in an equilibrium, right? You always have some R present. You always have some T present. They exist in equilibrium. The natural state of this is for the T version, the T conformation, to be higher than the R. All right, so in a regular inactive state, you're going to have more T conformation than R in this equilibrium. All right. In fact, you can define T and R as a ratio. So the ratio of T conformation to R conformation is referred to as L. Right? So initially, your L is high. All right? Now, let's say a substrate comes along. All right, and I'm going to have to go to the whiteboard here because I don't have a photo for this. I'm not as good at making drawings as the book is, so apologies if they're ugly. I messed that up. Okay, so that's my terrible attempt at drawing an enzyme. So that's our R. And it's in equilibrium with a T. I'm basically trying to mimic the shape of the ones in the book. All right, wow, that is ugly. Okay. But anyway, you get the idea. The different sites, all the potential different binding sites are differently shaped in the T than the R. So the R is more ready to bind something. So let's say, I'm going to focus in on this one right over here. So let's say you have a substrate that comes along, and it binds in this site, right? So basically what happens when a substrate comes and binds, and it's going to want to bind to the R, it's not going to want to bind to the T, right? Because we said R binds substrate much more tightly. What happens is it takes this enzyme, this exact enzyme molecule, chain, whatever, now it has a substrate bound to it. It removes this from the initial equilibrium, right? So you're taking R out of the equilibrium that it had with T. So remember our favorite principle, Le Chatelier's principle. We're taking R out of the system. The equilibrium has to shift in that direction. So as substrate binds to R, as R is removed, you try to replenish that R, and as a result, you end up reducing the amount of T that you have present. Okay? One second. Okay, so and that's an example. That's you can really see the example of positive cooperativity there, right? Substrate binds to R. R comes out of equilibrium. The enzyme, the T version of the enzyme, shifts conformation to make more R, which makes it more likely for it to bind a substrate, right? So the net effect is that binding of that substrate made it more likely for the enzyme to bind more substrate. And you can sort of see some interesting effects here in these two graphs. So if you look at the picture on the left, right, this shows the activity curves for an allosteric enzyme at different L values, right? So remember, L, when it's high, that's when you have much larger amounts of T as opposed to R, right? So let's look at L equals 10,000 here. If you look at the shape of the curve is much more sigmoidal when L is high and gets less and less sigmoidal as you go to 1. Right? So basically, the means the cooperativity effects are mostly seen when you don't have very much active enzyme, right? At that point, you can keep sort of slowly converting inactive enzyme to active enzyme, and you start seeing these shifts, right? Once you've really converted a lot of that T form to R form, then it almost resembles a Michaelis-Menten curve. All right, so net summary there, as L increases, you see more cooperative effects, and the curve is more sigmoidal. All right. The other picture there, that refers to something. Hold on. That refers to something called a C value. All right. So C value. First, let me define it, then I'll explain what I'm talking about. All right. The C value is the ratio of K sub R to K sub T. All right. So K sub R. Let me define these. This is sort of a mathematical value describing the tendency of the R form to release substrate. Right? It's very analogous, if you think about it, to the Ka, like in an acid dissociation constant. A Ka is the tendency of an acid to release its proton, while the Kr is the tendency of an R to release its substrate. All right? Same thing for Kt, except it's, well, T. Now, like I said, T is always going to be more inactive than R, right? R is always going to have more of a tendency to bind its substrate, and conversely, that means it's going to have less of a tendency to release it, right? So, no matter what, Kt is going to be greater than Kr, right? However, from enzyme to enzyme, the differences are not always the same. There are some cases, some enzymes where C is a smaller value than others, right? And you can actually see some interesting examples of that here as well. If you look at whoops. If you look at the part B here, the second photo,